I invite the next speaker, Engblom. He is a specialist in motion control and nanopositioning in the electronic and control group at Synchrotron SOLEIL. And he has been working the last few years in a SOLEIL MAX4 collaborative Nanoprobe project. He will present the result of the Nanoprobe project, metrology and control in stacked closed-loop systems. Christer.
Thank you. I will be talking about some of the results we had at the end of the last year, and I will be focusing on the metrology and control aspect of this. So I worked, as mentioned, in the Nanoprobe project, which was a 4-year collaboration between Synchrotron SOLEIL and MAX4. And we were tasked to produce a Nanoprobe end station prototype that we could do a 2D and 3D tomography on the nanometric scale. Now this prototype, it was supposed to have beam focusing stages, the central stop, double Fresnel zone plates, and an order sorting aperture, and with this a sample stage that would do the scanning. Now this came with a few challenges. One of which was we had to have nanometric resolution over millimeter range on the XYZ space. And with that, we had to rotate the sample full 360-degree rotation over the RZ space. And with this, have the typical stuff like step scans, fly scans, and have long-term stability, which is, in our case, roughly 8 hours. Now, the approach we took in the project was that we would have a stacked, compact, and a modular design. And we had a thing that we went with. We said that if we can see it, we can correct for it. Now that is more easily said than done, but we went for it by using interferometry for with stage characterization. And by that we evaluated linear drives using interferometry and rotational drives. Now rotational drives is a bit complicated to evaluate using interferometry, so we had to develop something in the project to do that. We also used interferometry in advanced modes of control, using the Delta Tau Power Brick LV as a controller, and the AtoCube FPS 3010 as an interferometer. Now the project in itself, it covered multiple domains. I was in electronics and control, but we had software and control, mechanics, optics and metrology, vacuum, and so forth. Now this is just a rough view of how the end station would look like. We had a beam focusing stages. I will be talking about the FZP stage. You can see here, it's marked in the middle of that, where each lens had a 5 degrees of freedom per lens. And I will be talking a bit about the sample stage that have 4 degrees of freedom. Now the CS and OSA stage, they both have 3 degrees of freedom, but we would use the knowledge of this FZP stage to build these 2 stages. Now the environment is very important, of course. We had to have a climate-controlled room. We made sure to have a marble table that we insulated in a special way to minimize XY temperature gradients. And we added water circulation and an enclosed space around the prototype for thermal impedance. Now the results we had from that were actually quite good. Just evaluating the environment, we were able to resolve better than 1 millikelvin resolution over a 1000 millikelvin interval. And early on, we found that a 1 millikelvin difference in temperature resulted in roughly 1 nanometer drift. So, as you can see in the graph to the right up there, over 8 hours, we found that temperature drifts were less than 10 millikelvin, which is actually less than 10 nanometers. Now this was without active stage installed yet. This was just in qualifying the environment before that. We're also able to qualify that XY temperature gradients were low and within specs. Now just a bit about the sample stage. We chose a stack design. You can see here the one to the left is a schematic of that. The bottom one is the X stage that was to be used mostly for fly scan. While the Y, Z, and the rotational axis would be used for step scans. Now on top of the rotation stage, we have 2 smaller X and Y stage for sample alignment. Now the thing of interest here is also, if you see number 6 there, it's actually a sample holder. But this also doubled as an interferometry reflector that would be used for sample tracking. Now this would since we have to do rotations, this would ideally be a cylinder, but we tried all different kinds. We tried cubes and different kinds of stuff. Now, for the control scheme for the sample stage, we had a cascaded one with an inner loop using the driver for each actuator. Some of them went up to 4 kilohertz. Now, the outer loop, we used a delta tau unit for that, and it's worked quite well because it had we could incorporate compensation tables, interferometric feedback, all in the native environment of the delta tau. We had Tango interfacing to the delta tau via Ethernet, so we could control it via high-level software. Now, this is our results we had with a 2D scan. It's a 1x1 micrometer XZ scan. Now, this is just running each individual drive with its encoder in a standard way that you would do things. Now, the one to the left, you see the error on the X, and the one to the right is the error on the Z. And you can see there's a slight waviness on the X-axis to the left, but it's still quite good, actually. We have an error of roughly 13.9 nanometers, and Z is roughly on the same magnitude. So what we did is we mapped the repeatable errors, and we put them in compensation tables. And you can see that the waviness on the X, they were greatly reduced, or to some greater extent eliminated, and we reduced the error to roughly 9 nanometers. The Z in this case, we didn't implement compensation tables because on this level they didn't have very good repeatable errors. And the next step and the best results is doing interferometer feedback, basically reducing the X error a bit more, but actually greatly reducing the Z errors. You can see it's down to 2.79 nanometers. The next thing we did is we ran a rotation on the sample stage. Now, this is just running a closed loop with the rotation stage, and I should mention that we had a small rotation stage that was piezo-driven, and this is running the encoder feedback on that. As you can see, just doing this, we actually don't even have nanometric precision. We have run out on X and Y at 1.25 microns. Luckily, though, the error was highly repeatable, and taking these and putting them in compensation tables, we were able to reduce error to 170 nanometers. So we took it one step further, of course, and we used interferometer feedback. And I should mention we used interferometer feedback and at the same time running compensation tables on the surface errors of the reflector. And by that, we actually reduced the error to 42 nanometers while rotating. So next thing, the fresnel zone plate stage. We chose a stacked and a parallel structure. Parallels just to create some movements in RX and RZ axis. And we had to have interferometry feedback. As you can see, you see the interferometry heads there. And it's actually a two mirrored identical module. So each holds an FZP. And the thing that is important for the FZP is that you should hold static stability over the course of roughly 8 hours. The control scheme of the FZP is also a cascaded one. I mean, we had an inner loop that was quite high frequency in this case. It was at 18 kilohertz. But the outer loop was a very low frequency one, where it's of a little tango, roughly 1 hertz or lower. We used Python scripts that did commands via Tango to get the interferometer feedback, and also use multi-axis control with kinematic conversions to do the control. Now, this is the stability over 11 hours with the FZP, and we have encoder feedback on the individual drives, but we're also having interferometer feedback on the X, Z, RX, and RZ. And this is a histograph, and you can see that 90% of this circle holds within 5.12 nanometers, which we were quite happy with. We also made sure to measure the stability between the FZP and sample, between the stages themselves. You can see here we have a setup. So it's between the green arrow and the red arrow. It's a bit difficult to do, but we managed within the project to find a Marray method of doing that using two overlapping repetitive structures. And using a microscope objective, we can actually see the results. So the uppermost graph, we see the steady state stability over 0.6 seconds, and we see that it holds over X and Y plus minus 5 nanometers peak to peak. We tried pyramid step scans on X. This one is a very small pyramid step scan, 10 nanometer steps. But you can see that on Y, it's not moving, and we actually have a quite nice decoupling on X and Y. The last graph there on the bottommost, showing the long-term thermal drifts, we could see that we had 60 millikelvin temperature increase during the 10 hours, which resulted in roughly 10 nanometer drifts on the x-axis. To summarize, we had good environment stability, and we were able to qualify and evaluate the sample stage using the different advanced modes of control. I mean, you can see in some cases, on the sample stage, using direct interferometer feedback, we're able to reduce the errors by 82%. But the best results we got was, however, with the rotation stage. I mean, as you saw, we had quite big parasitic errors on the rotation stage, and we were able to reduce them by as much as 96% or 97% almost. And thus having nanometric precision. We're able to qualify the FZP long-term stability and also verify the FZP stability in between. So, in conclusion, the concept proved successful. We can, with small modular stages, have nanometric stability on the sample stage, FZP stage, and in between. We can, on the sample stage, have XYZ scans with motion errors less than 10 nanometers, at least for the small scans that I showed before. And we can have sample stage rotational scans with motion errors at 42 nanometers or less. Of course, it is important to use stage characterization with interferometry that you incorporate with feed-forward compensation tables, and when you can, use interferometry feedback control. I should mention that interferometry, as it is, always has a limited working area. Now, in this case that I had before, we had, with this particular reflector, we had roughly a 400 to 500 micron area in which we had good interferometry feedback. We can increase this, however, by altering the sample reflector, maybe having a larger one or other modifications. If, however, we lose the beam, we still can use feed-forward compensation in the rest of the working area and thus still having nanometric precision. Now, I should mention that the scans that we did were actually at some point we're hitting the limits of our data acquisition system, which, if we were to use the Panda box that my colleague Xu Zhang presented yesterday, maybe we could have even better results. So that's it from me. I'm just showing some references if you would like to see with some publications we did within the project and a patent application. Thank you.
Questions? Yes?
I was wondering about the interferometry for the rotation.
Yes.
Is this a cylindrical mirror you're using?
Yeah.
Okay, and you can build this with this precision?
Yeah, we can. We put a lot of time to see the errors when you are rotating is actually quite difficult. Mm-hmm. And it actually was a big step to do in the project. So, but it is difficult, and it actually involves that you have to separate motion errors from surface errors of the reflector, which is difficult in itself. But it is doable. Once we had it working, it actually worked quite well.
And if I'm allowed a second question?
Yes. Except, no. Yes.
How long does it take to set up the experiment for the user?
That is something that would have to be looked into. We produced prototypes, but it hasn't yet been installed in the beamlines, so I cannot answer that. Yeah.
Okay. I have a simple question. How do you guarantee with this kind of extreme precision that your reference is not moving and you are not feedbacking some noise?
Yeah, that is a good question. What we did is we had our thermal guy and vibration guy qualify the environment, and we had to use a reference, of course. And our reference in this case, we had to use the marble table. And we qualified the marble table, and we made sure to verify the system with accelerometers and to make sure that there were no extreme thermal drifts. And we had to use a point of reference in this case. So, yeah, you're right. Point of reference is very important, though. So, yeah.
Where do you run the feedback loops?
Sorry?
Where do you run the feedback loops? Do you have a controller, FPGA, or?
Yeah, we do. We had the cascaded ones, and when we could, we put them in the drivers of the actuators. But the big control we did was in the controller, actually, controller level for the sample stage with the delta tau. But for the static or the slow corrections, we used the higher level, like Tango, to do the corrections.
But the fast one?
The fast one was in the delta tau level, I would say.
Yeah. So let's thank Christer again.